Today I'm going to be talking about modular superpixel tokenization for vision transformers and differentiable hierarchical tokenization. So these are we're going to start by talking about work that was presented at ECCV at the MELEX workshop. And then we're going to talk a little bit about our follow-up to that work. So yeah, without further ado. So first we're going to talk a little bit about what tokenization is and why it has a specific role in transformer models. So typically transformers were originally developed for language, and there the tokenization process is this is a way of minting or finding optimal ways to represent strings of text. And this process was kind of moved over to or inherited from the transformers for language in vision transformers. And here the solution in the vision transformer paper was to subdivide images into these uniformly sized patches. So this has a lot of benefits, but it also has some limitations. One of the limitations is that you get this low spatial resolution for the token representations. You're effectively downscaling the image by the size of the patch. These partitions that you get, they're uniform, but they also then ignore any type of structure that is inherent in the data. And it doesn't really leverage any type of redundancy that you might have in image data. For instance, if you have large areas that are homogeneous, then these areas will have exactly the same number of patches or tokens as a region that has more texture and more information. And you also have to fix the number of tokens for any given resolution. So what we ask is it possible to do anything better than this? Ideally, we would maybe like to have something where we get this pixel level granularity in the token representations. And we would ideally like for the tokens to adapt to individual images. So some sort of adaptive way of partitioning images is something that we've been thinking about. So what we discussed in the first paper that that was called the modular spitting image modular superpixel tokenization for vision transformers is that the tokenization pipeline can be split into three parts. So the standard VIT pipeline has this patch embedder where you partition the image into patches, and you embed these patches by a linear mapping, and then you add these positional encodings as well. So the way that we think about it is that this patch embedder can be extended to three components as well: a tokenization part that does the partitioning, a feature extractor phi that extracts features from these patches. And then there is an embedder module that embeds these patches and adds this positional encoding. So one of the things that by modularizing this tokenization process, we can generalize the VIT architecture to work with any type of partitioning scheme. And that's one of the things that we believe is one of the strong contributions of our first paper. So to kind of introduce what we're doing in SPIT, which is this superpixel transformer that we propose, is that we consider the image as like as a graph, and we have this signal function for each of the vertices in the graph. And this graph has horizontal and vertical edges. So we define a neighborhood of each vertex, and then we define some kernel. And in this original work, we used a cosine kernel. So for any vertex, we then define this V max. Any vertex V, we define this V max, which is the maximum, the maximally similar kernel in each vertex neighborhood. So essentially, we're looking at all the neighboring pixels or all the neighboring vertices in the graph that each we're looking at all the neighboring vertices in the graph, and then we pick the most similar vertex to each vertex. Then we construct this edge set using these most similar vertices, and then we take the connected components of the spanning subgraph under this edge set of maximally similar edges, and then this induces this graph contraction. So we get this next level of a graph where all vertices that are similar under the connected components are joined into a new vertex in the next graph, and the edges are updated accordingly. Then we compute new features where we just take the empirical mean of the features of all the pixels inside each of these superpixels, which is we now denote by S. And then we repeat this until we get some desired level of granularity. And this gives us this hierarchy of superpixels, and which is each of these levels is a partitioning, and they get coarser and coarser as we iterate over this process. So here we're illustrating this by showing an example where you see here you see that there are some pixels, and they have a similarity, and these dashed lines represent the vertices that are inherent in the graph, and the filled lines represent vertices that have been connected through this maximally similar neighbor connections. And then you see that this induces this thing where we have this graph on the left, which is more or less like a grid, like the original pixels. And then in the next step, we see how this becomes this, or under this connected components, we get this graph contraction where the graph is getting coarser. And in this first paper, we do this for typically four steps, and then we get something where we get the partitioning that has this desired level of granularity. So in this version of the work, the number of steps are fixed. So one of the challenges with this is that these superpixels don't align with how you extract features in a VIT. So we wanted to see if we could have something that is more or less interoperable with the standard VIT. And to do that, we align with these standard VIT features in the following way. We essentially compute the bounding box of each superpixel region, and then we interpolate that into a fixed patch size, which is usually typically square. And then we have take this mask of the foreground to kind of select just the pixels in this interpolated space that corresponds with the superpixel. And then we multiply those together, and then you get something that is has a fixed patch size, but also only corresponds to the pixels that were in the respective superpixel. Well, this is fine. There's, however, some issues with this. This mask is typically, depending on how the superpixel is constructed and its compactness and so on, we end up with, we have this potential that we can end up with something that is highly sparse due to this masking. In addition to that, we also have this thing where this interpolation loses some of the texture information in the patch. So our solution to this is to add these extra texture features from a gradient image. So we take this gradient image using some kernel, which is in the first paper, this is fixed. But we compute this gradient image, and then we take the joint histogram inside each superpixel region. And then we decide on a number of bins, usually the same as the patch size. So we typically pick Q by Q bins, and then we concatenate these gradient features to form a feature for each superpixels, which we denote by capital F here. And then in our experiments, we find that these gradient features actually improve both standard VITs and superpixel transformer models. In addition to this, we also have to solve this problem that we have with the positional embedding. So in a typical vision transformer, we have this learnable positional embedding, where each patch has a fixed positional encoding, which is added to their features after being projected by the embedder. So the canonical VIT embedding can then be described as this WF, where W is a linear mapping that we learn, and Q is this learnable position encoding, which for each of the patches, you have this vector that corresponds to this position. The problem here is that when you start using superpixels, this positional encoding is fixed to some sort of patch or image size, typically both, like the combination of patch and image size. So we can't use it out of the box. But what we can do is to use this kernel density estimator of the superpixel positions and take a linear combination of Q to form something that is more flexible. So for canonical VIT, we see that we can rewrite this and here we use this block matrix notation and see that we can kind of rewrite this as like a combination of two matrices, an outer product of two row-wise block matrices. So what we actually end up doing is that in this case, like for the VIT, you will get this. You will have that each position is unique. So essentially, you have that the positions will correspond to this identity matrix. But if we replace this with some HS, which is the KDE of these superpixel positions in the image, interpolated to some, or essentially scaled to some number of bins that corresponds with this Q, then we obtain this kind of dynamic kernelized positional encoding. And in this first paper, we use this Gaussian KDE to do this. So and we also show in this paper that like this corresponds with the standard VIT positional encoding. So here's a visualization of how this might look in the same example image as we saw earlier. Here you see that this mouth is the mouth of this boy is being we extract this region that corresponds to a superpixel and interpolate it to a fixed size of 16 by 16 in this case. Then this positional histogram, here we have this quite compact kernel, but you see that it gets a response for some of the positional encodings. And this positional histogram is then the linear combination of the positions that corresponds with the superpixel. In addition, we also see on the right here, bottom right, we see this gradient histogram, which is not particularly in this case, it's not a particularly strong response for anything, but these type of features seem to improve quite a lot, at least the superpixel tokenization, but also VITs, like I mentioned earlier. So what we do in the first paper is that we need some benchmarks, or we need some baselines, essentially, to compare against. So obviously we have this standard VIT, which is whose tokens you can kind of see on the left here. In addition to that, we also have this random Voronoi tessellation, which are not necessarily like that we add to kind of see how like other types of partitioning affects the model. So here, every time you like for those RVIT models, every time you want to tokenize an image, it generates this random tessellation of the image, which has nothing to do with the image content, but this gives you these irregular regions, or somewhat irregular regions. And then on the right, we have our spit model. So this image shows kind of how this image is tokenized by 3 different tokenizers. So our training pipeline kind of follows this paper by Steiner et al. That's called How to Train Your VIT. And what we're able to show in this first paper is that we get some slightly better K&M performance and slightly better performance on the ImageNet Real, but more or less across the board, you see that the performance is largely comparative to the VIT. So we don't show like a dramatic increase in classification performance, but we're able to show that at least it manages to keep the same level as the original. Yes, and we also ablate over some, or like we also do some transfer tasks for Caltech and CFAR 100. And for CFAR 100, we actually see there's some interesting results there, because CFAR 100 is a very much smaller set of images, or images with much smaller resolution. And here you see that these square patches actually align really well with the image, because superpixels don't align that well with very low resolution images, or they tend to converge really fast to square patches as well, sometimes miss a bit. So the standard VIT kind of outperforms the superpixel tokenization in the case of CFAR 100, low resolution images. We also did this thing where we wanted to have a look at how image saliency and attributions could be compared across these different tokenizers. So we also did some comparisons with an explainable method called LIME. There we also compute independent superpixels using something called SLIC, simple linear iterative clustering. So these LIME attributions on the right are taken with the same superpixels across all three tokenizers. But we see that the attribution maps from the superpixel tokenizer has much better, much higher granularity, and can capture pixel level details in the image. So you see here that these are the attributions for the class Banjo, and you see that all models kind of respond well to it, but you see that the VIT has this low resolution representation in the tokenized space, which makes it a little bit harder to use in dense modeling tasks, and also kind of makes these attributions a little bit less interpretable. So to evaluate these attributions that we get from these three different models, we use this comprehensiveness and sufficiency metrics. And here we find that our superpixel tokenized transformer performs better in terms of when compared to LIME in the case of comprehensiveness. All other models are kind of worse off than LIME, so the explanations you get out of the standard VIT and the random Voronoi tessellated VIT are kind of slightly worse. However, for the superpixel model, you actually get attributions that are more faithful than LIME, which we saw as something that is significant. In addition to that, we also did this salient segmentation. Here, the task is to determine which regions of the image correspond to a foreground and which correspond to a background. So you want this mask to kind of capture the foreground elements of an image. And this is it's not just unsupervised, it's more or less zero shot, because all you do is that you use this the attention, well, you take tokenized representations at the end, and you use token cuts, essentially, by a spectral graph cut method that enables you to kind of easily determine what the foreground and background is. And our model performed quite well, because we don't need to do any type of upscaling, because the superpixels themselves correspond to the image with pixel level granularity. So we achieved quite good results in this zero-shot salient segmentation task. In addition to that, we wanted to see how strong these features were and how they correspond across different images. So we took this, we compute the PCA. Well, actually, what we do first is that we use the salient segmentation to get to find the foreground of each image. And then we essentially so then essentially what we do is that we see, like, look at the feature correspondences and for each token, and then we map that using PCA, and then we have like we can kind of visualize how strong, like, which features correspond to one another in RGB space, and then we visualize this here. So we also wanted to look at the tokenizer generalizability. We want to look at what the effect was of swapping the tokenizer on swapping tokenizers between trained models. And what we found is that these patch-based VITs, or the canonical VITs, they struggle with these irregular partitions, which makes sense. They haven't been trained with them, etc. We see that these superpixel, like our superpixel tokenized transformer and this random Voronoi tessellated transformer, they generalize a little bit better by virtue of having this being trained with this tokenizer that has these irregular regions. And then we, like, for this random Voronoi tessellation, we had a slightly surprising result where we see that it actually generalizes really, really well when it has these improved, like when we have these joint histogram gradient features. And also the spit model generalizes quite well. However, the random Voronoi tessellated model does slightly better than actually it improves when you go to the square patch size, as you see in the fourth row here. So that was quite interesting. Okay, so for this superpixel tokenized transformer, or for superpixel transformers, what are the pros and cons? Well, some of the really beneficial things from this construction is that our framework kind of holds for any partitioning scheme. You can kind of decide on some way of partitioning the image, and the model will be able to work with that, and you can get something that works as well as a vision transformer. We also get, like, comparative results for image level classification, and we show that we get this better alignment with dense prediction tasks. And in addition, we also see that the saliency maps produced by attention maps correspond much better with explainability methods, or you can kind of use these explainability methods on the tokenized representations themselves, which improves the resolution of your representations. So some of the limitations, well, superpixels aren't necessarily free. It costs something to do these computations. However, we managed to kind of keep that cost quite low in this paper, because we're not really learning the superpixel tokenization, which is also kind of a limitation of this first paper that we proposed. Also, we're not fully utilizing this hierarchical structure of the superpixel tokenization. As you might recall from when we discussed how this superpixel tokenization was performed, you saw that we get this hierarchy. And the problem, or like one of the limitations of this approach that we presented in the first paper, is that we're not really utilizing the hierarchy other than computing it up to a certain level, and then and after that we kind of just stop and use that as our superpixel tokenization model. Also, these superpixel tokenized VITs, they also require gradient features. These gradient features are almost required to get enough texture information to do the same as standard VIT. But these gradient features also improve the patch-based VITs. So, to kind of to follow up on that work, we wanted to implement some differentiable mechanisms into the existing framework. And we wanted to utilize the full superpixel hierarchy with an information criteria. And then we also wanted to do some retrofitting of existing VIT models by re-adapting them for new tokenization methods. And then we also wanted to show some capabilities for image vectorization. So the question then is like, how can we add these differentiable mechanisms from this tokenizer into the VIT features themselves? What we propose is this lightweight CNN feature extractor, which is typically 2 or 3 layers deep, very small, but has the same resolution as the input. So it's almost like a small half UNet. And then we weigh these the token aggregation that we did in the original superpixel, in the original paper. We add weights from this kernel that we use to aggregate the features, meaning that we kind of add some learning signal from the differences or like similarities for each superpixels into how the superpixel aggregates, meaning these superpixel features get gradient information from the CNN. Then at the end, once we have some sort of superpixel partition, then we use this mean injection trick where we essentially take the original pixels of the image, subtract the mean of the superpixel that it has, or like the mean color of the region that it belongs to. And then the mean is replaced with, it's essentially replaced with a prediction of the mean from the superpixel tokenization itself. So these superpixel features that we use to aggregate in the tokenizer is then projected back and will kind of replace the mean of the original pixels. So in that way, we kind of get an image that has features from the tokenization process built into it. So when we interpolate, these features will be inherent in the image. So the VIT will have gradient signals from the tokenization process. So yeah, so the next thing we want to do is to incorporate something called model selection to utilize this full hierarchy. And there are several papers on this multi-scale adaptive tokenization, which is where you typically in these type of works, you want to decide on some level of granularity for each region in the image. So for regions that have a lot of redundant data or have little variance, you want to maybe have a bigger patch. And for smaller regions, you want to have a smaller patch. One example of this is this quadformer paper by Ron et al. 2023. And they use this variance reduction criteria, which is similar to how binary trees work. Yeah, if people are familiar with that. So building on that, we wanted to go one step further and use classical information criteria. And the benefit with that is that you don't have to threshold, or the model doesn't have to learn what type of level of variation should be inherent in each patch. Instead, you get this penalty term from the degrees of freedom. However, we don't really have any type of firstly, you don't have any type of, you first have to kind of define a likelihood, but that's not very problematic. We can kind of just consider a superpixel partition as a piecewise constant model of the image X. And then this likelihood more or less corresponds to a variance reduction criteria with some extra constant terms. Then for the degrees of freedom, you have to kind of consider how many parameters are inherent in the model. And their parameters for the superpixel model of the image corresponds to how many regions that is going to be used in the model. So how many patches you use. We can't really estimate that very easily, but we find that, or what we find is that we can estimate it, but we have to use some theory from lattice theory, or we use theory from lattice theory to find that we can get an estimate of degrees of freedom by using the volume of the region given the graph, which essentially corresponds to the number of edges in the original edge set that is also included fully in the superpixel. But that using that gives us a way that we can kind of use this information criteria to prune the tree. So the next step we want to test out and experiment with is how well pre-trained VIT can be retrofitted to a new tokenizer. So in order to do this, we first pre-train the tokenizer itself with this reconstruction loss, where we essentially want this from the superpixel tokenization process. We want this CNN and this linear projection at the end to correspond more or less to the image. And during this process, the tokenizer will learn that certain regions are better, like it will learn to partition the image optimally, and also to project these features from this CNN or this latent space back to something that corresponds to RGB, more or less. In addition to that, we also do this dynamic masking, where we introduce this lambda and this beta parameter as learnable parameters for our feature extractor. And then we use this weighting of the foreground and background masks in addition to this extra beta parameter to essentially weight the contribution of this background mask in each superpixel. And this might seem a bit complicated, but it's actually quite easy. The only thing that the model the only thing that we're adding to the model is kind of a mechanism for it to kind of decide on how much of the surrounding region of each superpixel that is to be included in the features. So the model here kind of learns to select some level that it prefers of background features, or these like sort of a background mask that is also learnable. And this improves the convergence of this of the retrofitting process quite a lot. But it also adds this extra level of dynamic learning to the model. Then we fine-tune this retrofitted model on some downstream task. Typically, we fine-tune on classification first. So here's a visualization of this pipeline. So at the top left, we can kind of see this input image. Here, we have this nice image of a pony. And then this goes through the CNN on the right, getting some increased feature dimension. So we get these features. And then what we get is, like, we pass this through the tokenizer in this embedded space of extra features. In this way, we build the hierarchy. And here we build the hierarchy all the way to the top. And from here, once you have the full hierarchy, we use this information criterion to select an optimal partitioning from the hierarchy. And that gives us a superpixel partitioning and a set of features. Now, from here, we subtract the mean using these superpixels, which corresponds to this branching path on the left from the input. And we get a set of residuals that we combine with this mean injection trick to get this some features. And then in this feature extraction, on the figure on the right side in the feature extractor space, you see that how we combine the foreground and background masks with the feature from the image and this extra background mask feature that we also use. Yes. So yeah, there's a lot of moving parts, but in the end, we get something that is differentiable and is able to kind of learn to partition images in an end-to-end fashion. We have some nice results for classification. In most cases, we find that the retrofitted VITs improve a little bit on performance in classification tasks. We also see that when we train a model from scratch using this dynamic way of computing the features, we actually managed to improve quite a lot from training a VIT from scratch using the same setup. So yeah, one of the things that we kind of have to accommodate a little bit for is that we like using mix-up, which is a feature like an augmentation method for images. Like mix-up will kind of get in the way of the tokenizer learning meaningful regions. Therefore, we dropped that, and that also might be one of the reasons why the full trained models get slightly worse performance than the retrofitted models. But anyway, like the takeaway message here is that this works, and it in some cases it does improve the classification results, and they're quite competitive. In addition to that, we did some semantic segmentation on AD20K, and there as well we were able to show that just by here we can kind of do prediction on the tokens themselves without having to do any type of upscaling or any type of adding more sophisticated decoders. And we're able to show that we can actually get quite competitive results for semantic segmentation on AD20K just by predicting on the tokens from the Superpixel transformer. Here are some example images of some feature correspondences similar to the ones that we saw before, and something that visualizes some of this, like the segmentation. Here, these images are scaled up quite a bit, so we have more tokens than the transformer is used to seeing, and it also isn't able to. Well, yeah, it's just larger images. But yeah, we see that the feature correspondences align quite well across the images of the cats. And at the bottom, we see that the segmentation maps that we get are also quite good, or qualitatively at least, look quite impressive. In addition to that, we also find that pre-trained tokenizers using our differentiable hierarchical tokenization methods can be used to extract these vector graphics, extract a vector graphic representation of a rasterized image. So here we just apply some off-the-shelf shape vectorizer to each superpixel, and then construct this SVG from these tokens directly. Here we see like the original image on the left, and on the right we see this SVG where we have zoomed in on some relevant parts where you can kind of see that the regions align quite well with the original image, giving really high quality vector graphics. And here we also compare our method with some state-of-the-art vector image vectorization methods. Here we compare our method with diffvg, and it turns out that we get in certain areas we get much better representations with slightly more paths than the diffvg method, but it's more or less comparable. So we get this competitive performance compared to more advanced methods. Okay, so to conclude, like we show that you can kind of retrofit a standard VIT with this new tokenization framework that is end-to-end learnable through some downstream task. We get comparative results in both image and segmentation tasks, image level classification tasks and segmentation tasks. And we get this image vectorization capabilities out of the box. And our method can improve the duplication for large, especially for large and higher dimensional images. The downside is that, again, we have some computational overhead in training and inference, particularly due to the CNN that we add. It adds some overhead, and there's definitely room for improvement in how we do the feature extraction, how we embed the gradients, and so on. And it works, but it might be it might lead to some computational overheads. So, and also we've currently only tested our framework in supervised learning frameworks, and that's one of the things that we're looking to expand on. And we're also looking to kind of leverage the hierarchy in the transformer itself. So we're looking at these types of extensions to our current work. So yeah, I just wanted to also, at the end, I also just wanted to mention my collaborators. So in this original paper, Superpixel Tokenization, Modular Tokenization for vision transformers, I have my supervisor team that was very helpful in helping form the idea and write the paper. I'm very grateful for that. And for this other paper, I'm working with a team both from here, from UIO, some people from UIT, and also with a collaborator that I also have in Milano. So we're hopeful, and yeah. Thank you very much for your attention. The QR code in the top right is a repo if you want to have a look at this original Superpixel tokenization, the code for the original Superpixel tokenization method. Thank you very much,